this FRQ, we have a chemical reaction, and the function for the chemical reaction satisfies the differential equation here. We want to use the line tangent to the graph at t equals 0 to approximate the amount of the substance remaining at time t equals 2. So we have our initial point basically to make our tangent line with. So we have the point 0, 10, because at time 0, 10 grams. We have our slope. dy dt equals negative 0.02y squared. At time t equals 0, our slope is then negative 0.02 times 10 squared. Negative 0.02 times 100 is negative 2. So that's our slope. For our equation of our tangent line, we use point slope like we always do. Y minus 10, again using this point up here, equals negative 2 x minus 0. So now what were we doing? Approximating the amount of the substance remaining at time t equals 2. I screwed something up here. Maybe you see what it is. This isn't an x. Our independent variable is t. So now we can use our point at t equals 2 seconds. So y minus 10 equals negative 2 times 2 minus 0, because we have our independent variable and we want to solve for y, which is the amount of the substance remaining. Y minus 10 equals negative 2 times 2 minus 0 is just 2. So y minus 10 equals negative 4. So y equals 6. So there are 6 grams remaining at t equals 2 seconds. Part B, same problem. We want to know whether the graph of f, which is our function we're dealing with the chemical reaction, could resemble the following graph. So looking at this, I think first it's kind of like, how would I know? But let's look at our derivative. So dy dt equals negative 0.02 y squared. So let's think about how this behaves. Negative 0.02 is a constant, and it's always negative. Y squared is always positive. And so if we multiply a negative times a positive, who cares what they are? Negative times positive is always going to be a negative value. So this means f is always decreasing, because the derivative is always negative. Now, if we look at this function over here, it's not true. If you look right here, that's increasing, has a positive slope, or the tangent line has a positive slope. So since f is increasing, or rather not since f, since the graph is increasing, and f is always decreasing, this cannot be a graph of f. Part C. Find an expression for y by solving the differential equation. So now what we'll do is split the variables. So let's make this dy over y squared. On the other side, we'll have, and again, we're starting with this, we'll have negative 0.02 dt. Before I integrate, I'm going to rewrite this as y to the negative second dy. It's nicer to integrate. You can just do that in your head too, but equals negative 0.02 dt. Now let's integrate both sides. So we get negative y to the negative first power equals negative 0.02 t plus c. This is the same as negative 1 over y is equal to negative 0.02 t plus c. So now we can keep solving, or we can find c now. I'm going to solve for y first, but again, it really doesn't matter which way you do it. So if we solve, first I'm going to multiply both sides by y. So I have negative 1 is equal to negative 0.02 t plus c times y. And we're really just switching it, so this other part of the function is in the denominator of a fraction instead of the y. If we divide both sides by negative 0.02 t plus c, we end up with y equals negative 1 over negative 0.02 t plus c. Now let's use our initial condition of 0, 10. So y, which is 10, is equal to negative 1 over negative 0.02 times 0 plus c, meaning 10 is equal to negative 1 over c. Multiply both sides by c. 10c is negative 1, so c is negative 1/10. So now going back to our initial equation here, now I can plug in my c. So y equals negative 1 over negative 0.02 t minus 1/10. Ugly fraction in a fraction, but we can totally keep it. My inclination is to write it as y equals 1 over 0.02 t plus 1/10 to at least get rid of the negatives, but either one of those is just fine. Finally, for part D, we want to know whether the amount of the substance is changing at an increasing or a decreasing rate. Whenever I hear at an increasing or decreasing rate, I think acceleration. So in this case, we know dy dt equals negative 0.02 y squared. This is like our velocity. So this is our rate of change. But now the rate of change of the rate of change, we take the second derivative. So d squared y over dt squared. And this equals negative 0.04 y times dy dt. Conveniently, we have dy dt. It's right there. Yay. So d squared y over dt squared is negative 0.04 y times negative 0.02 y squared. So d squared y over dt squared, or the second derivative, is, well, negative times a negative is a positive. 0.04 times 0.02 is 0.0008. And then we have y times y squared, which is y cubed. So this value is always going to be greater than 0. The reason is because y has to be greater than 0, because you can't have a negative amount of something. Okay? So if our second derivative is always greater than 0, which is essentially our acceleration, and just to back up for a moment, we also know that the amount is decreasing because this rate is always negative, which we already talked about. So since dy dt is less than 0, always, And the second derivative, d squared y over dt squared, is always greater than 0. The amount of the substance is decreasing, hence this negative. This is less than 0, so it's decreasing at an increasing rate, because the rate of change, or the acceleration sort of, is always positive.